In electronics, from analog to digital, we need timers. A timer, as its name suggests, it's a device that gives a signal at a stable or variable frequency. Even though there's a big amount of devices and methods to generate signals as timers, today we're going to analyze one of the most important and influential timers of all time, the 555 timer. The 555 timer was invented in 1971 by Hans Kamensit and produced for the first time at Signetics in 1972. The fundamental way this timer works is by charging and discharging a capacitor, which size or charge capacity determines the output frequency. Let's analyze the internal structure of the timer. The timer in its individual form has 8 pins. The first pin is ground, the second pin is trigger, the third pin is output, the fourth pin is reset, the fifth pin is control voltage, the sixth pin is threshold, the seventh pin is discharge, and the eighth pin is VCC or supply. Now we have the internal structure. As you can see, the structure is quite simple. We have two comparators, which rely on the voltage dividers that are internally, and the reason why the timer is called 555, because we have three resistors of 555 kilo ohms each. We have a flip-flop that gives the output square wave, a NPN transistor connected to discharge, which discharges the capacitor when activated, and our inverter buffer at the output. Before we see the timer working, it's necessary that we check the datasheet to comprehend its behavior and limitations. Let's begin with the pin description. Pin 1 is ground. Pin 2 is trigger. It's responsible for making the flip-flop transition from set to reset and vice versa. The timer output relies on the amplitude of the pulse given to this pin. Pin 3 is output. Pin 4 is reset. It indicates that a negative pulse deactivates or restarts the timer. When not used, it should be connected to VCC to avoid false triggers. Pin 5 is control voltage. It controls the threshold and levels of the triggers, determines the width of the output wave, and external voltage can be applied to this pin to modulate the output wave. Pin 6 is called threshold. It compares the voltage applied to this terminal with a reference given by the internal voltage dividers at a level of 2/3 VCC. The amplitude applied to this terminal is responsible for manipulating the flip-flop state. Pin 7 is discharge, the output of the open collector that discharges the capacitor between intervals, in phase with the output. It changes the output state from high to low when the voltage rises up to or above 2/3 of VCC. Pin 8 is VCC or positive supply. Then we have the electrical characteristics. For supply voltage, we have a minimal value of 4.5 volts and a max value of 16 volts. For current consumption, which means the current required by the timer to work properly, it's defined as 3 to 6 milliamps, with a supply of 5 to 10 volts, and 15 milliamps with a supply of 15 volts. For the accuracy, we have that the main factor is temperature, with an accuracy of 1%, and followed by values of 3% per temperature increase, and 0.3% per volt. Before analyzing the function of the timer, we can see a comparative between the block diagram and the internal diagram. We can see that it is composed of bipolar transistors and resistors, which defines the high consumption of the timer. But we also have to remember that the timer has been almost the same since it was made in the 70s. Now, let's dive into the functionality. As the definition of the timer, it offers a clock signal that can be from microseconds to hours, depending on the capacitor and resistor values given in the circuit. The timer can operate in two modes, Astable and Monostable. Monostable refers to the mode in which the timer functions as a one-shot timer. The capacitor is initially discharged by the discharge transistor, and once a negative pulse lower than 1/3 of VCC is applied to pin 2, the flip-flop is activated, which deactivates the discharge transistor and the output is set to high. The voltage through the capacitor is incremented exponentially for the period of t equals 1.1 Ra times C, which at the end of the period equals to 2/3 of VCC. The comparator then restarts the flip-flop, which then discharges the capacitor and sets the output to low. Do you have a project that needs to be finished? Do you have an idea for a product and you want to take it to the next level? We are your best choice. In PrismaSem Network, we have the best team to do so. We offer services on hardware design and software design. From PCB development, firmware development, app development, and desktop development. We offer competitive prices and an excellent service. Contact us to get a quote. All of the info available at the video description. So, here we have the Monostable 555 configuration, and we can see that the output is only given when we have the one shot, in this case being the button we have on the proto board. And in the oscilloscope we see the output signal, which in the top signal is the square wave of the 555 timer, and below we have the discharge and charge wave from the capacitor. So this is why it's called one shot, because we have to press or we have to give a signal to activate, and the output is only going to be given once. Now, the Astable mode refers to the function method in which the timer is running in free mode. This is because we connect pin 2 and 6 together, which turns the timer into a multi-vibrator. The external capacitor is charged through the resistors A and B, and then discharged through RB. Then the pulse width will be an accurate relation between both resistors. In this mode, the capacitor will be charged and discharged between 1/3 of VCC and 2/3 of VCC. Just like in the trigger mode, the charge and discharge times, as well as the frequency, rely upon the operation voltage. Having the following formulas of frequency and duty cycle in the screen. Now we have the Astable configuration. We can see that we have an output despite not having an external trigger. And we can change the frequency with RA and RB, in this case being both potentiometers, so that we can change its value in real time. And we can see that the frequency is being increased we can see the output waveform. Also the pulse width is being modified. As we can see, we can also modify the pulse width, increasing or decreasing the off time. And with this resistor we can change the output frequency. Remember that the top signal is the output of the 555 timer, and the signal below is the charge and discharge of the capacitor, or the pin 6. Well, now that we have analyzed the timer functionality, it's time to ask the important question: is it still relevant? This timer, despite being revolutionary in its prime days, is no longer relevant due to the digital electronics boom in the past 2 decades, with devices such as microcontrollers where we can output waveforms defined by firmware and not with analog components. This makes the timer quite rudimentary. But despite this, the timer is still very easy to implement, cheap and easy to get. It's an obsolete component that may or may not be seen in modern designs, in contrast to the old days where it was seen in many applications. This is why most of the modern applications are in the learning or hobbyist scene.